So in this question, I have three ballot boxes. They are connected by cords, one of which wraps over a pulley having negligible friction on its axle and negligible mass. The three masses are MA equals 30 kilograms, MB equals 40, and MC equals 10. When the assembly is released from rest, what is the tension in the cord connecting B and C, and how far does A move in the first 0.25 seconds, assuming it does not reach the pulley? So I'm gonna go through steps as usual when I solve problems on forces. The first step being drawing the free body diagram. But because I have three blocks here, I'm gonna first decide which block to study and which block I will need to draw the free body diagram for. What I will do is that I will really take things very basically. I will draw the free body diagram of all the blocks and then decide which one to use to solve the question, which is asking for the tension between cords connecting B and C. So I'm starting with step one, which is drawing the force diagram. Now here I have multiple objects, so what I did was I drew all of them now. I'm just taking it things basically from a very basic approach, and then I will select one of these objects to solve for the question. So for block A, I have a downward weight force and an upward normal because block A is on a surface and block A is being pulled by a rope, so there's a tension force acting on it. For block B is hanging, so it will not feel a normal force. There's an upward tension acting on it, and there's the downward weight. Block B also has a cord attaching it to block C, so there's a tension there between B and C. One thing I want you to notice, the tensions along either side of B are not the same. This is an important comment. The tension will be the same only along a cord that is not interrupted by a mass. So looking at my figure, I have the cord running between all these three objects. If I consider this rope here, the tension here along this rope will be the same, but it will not be the same as on the cord between B and C, because now the rope is interrupted by block B. Once the cord or the string is interrupted by a mass, the tension will change. So the tension here has a certain value, and here between B and C, it will have a different value because now it is interrupted by a given mass. So the tension here will be different. I can write this down. Tension along the yellow part is same, and tension in the pink section is different than the yellow one. Notice that in this problem, we are told that the pulley is considered massless. So that's why I selected the whole cord, including the pulley. The tension will not be changing across the pulley because it is massless. So this means that the tension that I will draw on this side here will be the same as the tension that block B will feel here. If I draw the forces on block B, the upward tension that is from the yellow section of the cord, I will label it as T, which is the same as T felt by block A. Now B feels a tension from the lower pink section, but this is not gonna be the same as the tension above it from the cord that is on top. So I will give it a different labeling. I will name it TBC. It's the tension between blocks B and C. And then there's also the weight of B, and these are basically the forces acting on block B. Block C will also feel a tension force. The tension that block C feels is over here, which is basically in the pink section. So it is basically TBC, not T. So I labeled the tension on block C to be TBC, and there's also the downward weight. So I got these nice 3 free body diagrams. My system is released from rest, so it's moving now. Obviously because I don't have a friction on my surface. So the system will start to move immediately when there are hanging objects on the right-hand side. So because the system is going to be moving, there is acceleration involved. I always like to draw the acceleration vector in the free body diagram, because then when I find x and y components, I can also find x and y components for the acceleration. So I'm going to really draw the acceleration vector. Block A will move to the right, so its acceleration vector will look like this. Block B will move downwards, so this is its acceleration vector, and block C will also move downwards. Now, one thing I want you to also notice, for this system which is attached by cords to move together, the accelerations must be the same. Otherwise, the cord is going to be detaching. The blocks will break from each other. So these accelerations must be the same. So I will label them all as the acceleration A, and that's it. I will remove the subscripts because they all have the same magnitudes. The directions are different, by the way. Block A is to the right, blocks B and C are moving downwards. So, so it's gonna be convenient to just distinguish that the magnitude is the same, but not the directions or the vectors. So I drew my free body diagrams. The question asks me for the tension in the cord connecting B and C. So what I really want is TBC. That's what I want. So now I'm gonna select my free body diagram accordingly. So it's gonna be convenient to study block A or B or C according to what I want. I want the tension between blocks B and C. So I would start with selecting the free body diagram of block C because it contains the tension I'm interested in, and it has less forces than block B, so maybe it's easier to study. I consider block C then. For block C, I will use Newton's second law because my system is accelerating, and I will project that along the y-axis because all of the forces are vertical. So this gives me sigma Fy equals MAY. Everything that is upward is considered a positive force. Everything that is downward will be considered as a negative force. If I had any oblique forces, then I would have to project with sine theta, but here luckily I don't, so things are easy. I will have plus TBC minus WC equals minus MA. I put a negative sign in front of the acceleration because the acceleration is downward. And like I said, everything that is downwards, I will take it to be negative. I end up with this equation. I will rearrange for TBC, which is what I want. TBC will be equal to WC minus MCA. So this is my equation for the tension between blocks B and C. However, I cannot really get a final answer from this because I don't have the acceleration of the system. This will push me to study block B. For block B, I will have an additional force, which is the tension force. I make a similar study. I'll have plus T. The tension between B and C here is downwards, so I'll put minus TBC. I have the weight also downwards, so minus WB. This is equal to minus MBA. So again, the acceleration is downwards, so I also put that to be negative. But my problem here is I don't have the tension or the acceleration. And this is what I want, TBC. So I ended up with having one more unknown, so this wasn't very useful. I will consider block A. For block A, we have two directions for the forces. The tension is horizontal and the weight is downwards, and the normal is upwards. However, I will study the horizontal direction because this is the direction that contains the acceleration and the tensions. And along the vertical, I'll just get N equals WA, by the way. It will not give me anything useful. So I will study sigma FA equals MAX. Along the x-axis, I only have the tension force. So I put plus T, everything to the right, I consider it to be positive. Everything to the left, I'll consider it to be negative. The acceleration is also to the right, so I'll put plus MA as well. I end up with this equation. Now, looking at all three equations, I see I have three equations with three unknowns. So maybe I can work with these and solve for the question, just reduce the unknowns one by one to be able to solve for the tension in BC. I'll just add one more slide so we can continue here. I'll copy the equations we got for now. Here we go. So what I'm going to do is I'll try to solve for TBC. Namely, if I'm able to substitute the acceleration A with something I can calculate, then I can work with solving for the tension. So the first thing I will do is I'll try to get rid of the tension here by substituting MAA. So I'll substitute this over here. I will get MAA minus TBC minus WB equals minus MBA. Then I'll rearrange this equation for the acceleration. So I'll isolate the acceleration alone and the rest on the other side to get rid of the acceleration here. Once I get rid of the acceleration here with something I can calculate, I will be able to find this tension between block B and C. So this is A. Isolating it, I'll get, well, what I will do is I'll keep MAA here, bring this to the left side. And on the right side, I'll have WB plus TBC. And then I'll take A as a common. I'll get WB plus TBC over MA plus MB. I will substitute this here. I'll get TBC is equal to WC minus MC into WB plus TBC over MA plus MB. This gives me, so I want to solve for TBC now, but I have TBC here and in the right side, so I'll isolate this one, bring it to this side. I'll get TBC plus MC TBC over MA plus MB. You can see this, what I did basically was I expanded and separated the quantities in the denominator. And then I took this whole term to this side. And the rest remained in the right side. So what remains is WC minus MC WB over MA plus MB. Take TB as a common, TBC, and 1 plus MC over MA plus MB equals MCG minus MC WB over MA plus MB. I'll get going to another slide. Okay, so I remind you what we want is the tension, TBC, and I just actually got to some answer, which is all in terms of the masses, if you notice. And I can solve for the tension now. The masses I have are all I need. MA is 30, MB is 40, and MC is 10. Let me just double check. Yeah, this looks good. So now we can really calculate the tension force. Write down its magnitude. So I calculated this. I got the tension to be 36 newtons between blocks B and C. So this is the answer to part A. In part B, we're asked how far does A move in the first 0.25 seconds? So the word how far, this means I want the distance covered by block A in a time equal to 0.25. To find the distance for block A, I will use kinematics. I'll use half AT squared plus V0T. So here, one thing I know, the system is released from rest, so this is really zero. And to solve this question, I will solely need the acceleration. Now, previously I got some expressions for the accelerations. So the acceleration A can be either written as A equals T over ma. However, this tension, I didn't really end up finding it. So this is not going to be very useful. Rather, I will use equation 1. Let's look at equation. Equation 1 contains the tension between B and C, which I just found, and the weight. So both of these, I really have them. So I'm going to be using these. This equation will be useful to find the acceleration which I need in order to deduce how far block A has moved. So I'll just use this equation. And I will get A. A will be WC minus TBC over MC, which is MCG minus TBC over MC, which is 10 times 9.8 minus 36, which I found in part A, over 10. I'll deduce the acceleration. This is the acceleration of my system, and I can use that to deduce how far block A has moved in 0.25 seconds. We will get 0.2 meters. So here we have a similar problem, two blocks connected by a cord. It passes over a frictionless pulley of negligible mass. The arrangement is known as Atwood's machine. One block has a mass M1 equals 1.3 kilograms. The other has a mass M2 equals 2.8 kilograms. I want the acceleration and the tensions. If you take a look at our figure, I marked this cord by a pink line. As I told you before, the tension would be the same across the whole cord if this cord is not interrupted by a mass. Across this pink section, I only have the pulley which is massless. So I can now deduce that the tension is the same across the cord, and thus the tension on this block will be the same as this block. That's the first trick in such problems. And the second thing I need to be aware of the acceleration. To keep the system moving together, the acceleration has to be the same for both blocks. So I'll just write that as A. I will also have some weight forces, M1G and M2G. I got my force diagrams. The only thing that remains is to just notice that the acceleration for block 1 will be upwards, whereas for block 2 it will be downwards, because M2 is heavier, so the system will be moving clockwise, M2 will move down, M1 will be lifted up. Now I will move on to the equations. Newton's second law is used here because I have an acceleration. For block 1, I will get minus m1g, everything that is downwards, I give it a minus sign, plus the tension, which is upwards, equals plus m1a. The acceleration is upwards, so I'll put a plus sign here. What I want is the acceleration in part A. If I try to solve for the acceleration, you will see that I have the tension as an unknown. I don't know this. So I'll try to solve for block 2 as well, and perhaps equations with two unknowns. For block 2, I have minus m2g, weight is downwards, upward tension again, and it's the same tension. Notice how being aware that the tension is the same has saved me some time in my equations. I can directly see that this tension is the same as this. And I'll get here, I get minus m2a for block 2. What I will do is for block 2, I'll get an expression for the tension, and I will plug it here. I will get A is equal to minus M1G plus minus 2A plus M2G. Of course, here I have, this is over M1. As you can see, I have the acceleration on the right side and the left side, so I will isolate it. Take this term to get A plus M2A over M1 equals M2 minus M1G over M1. Just combine these two together. I'll take A as a common. I'll get A is equal to M2 minus M1 over M1 into 1 plus M2 over M1 times G. I'll expand this, it will look more simple. I got an expression for the acceleration, which I can easily solve for. Thing I want you to know, this system is called the Atwood's machine. It's an experiment that you should usually see in the lab. And what's interesting about it is this expression for the acceleration, you can always use it whenever you see this kind of arrangement. Like whenever you see these two masses hanging with one cord and a pulley between them, the acceleration will always be the heavier mass minus the lighter mass over the total mass times gravity. So here you will get around 3.6 squared. This is for part A. And part B, we just want to find the tension. So I'm gonna just use my expression for the tension from here. So this is the expression I got for the tension. I'll just use that. I have M2 is 2.8. I got for the acceleration 3.6. I will get 2.9 newtons. One thing I want you to notice, we got a positive sign for the tension, which means it is upwards. Let's take a look at our figure. Yes, indeed, the tension is upwards, so the math is matching with the physics, and this looks nice.